So far in this course, we have covered classification and regression models and advanced machine learning concepts. We also have in-depth knowledge of building predictive models with the Caret package. All of these fall under the category of supervised learning, where you have a response variable to predict. In unsupervised learning, a response variable is not needed. In this section, we will deal unsupervised learning techniques such as principal components analysis, clustering analysis with k-means, and principal components. We will also see useful topics such as clustering tendency and finding the optimum number of clusters. We will understand and implement hierarchical clustering and affinity propagation. Finally, we will understand various recommendation algorithms and build recommendation engines. Let's begin the section with principal components analysis. In this video, we will understand how PCA can be used as a tool to reduce dimensionality of the data. That means we convert a lot of features to a few principal components. We will also see how to implement it in R and interpret the results. We know that each row in a dataset conveys some information in that observation. This applies to every other row. What you may not have realized is that the total information in a dataset is the amount of variability it contains. When you have a large number of features in the dataset, some of them could be correlated. Using PCA, you could explain a large part of the variation in the data in fewer variables, called principal components. It's like compressing the information in your large data set. An important note is that unlike predictive models, the principal components explain the variability in the original data set and not the response variable. Let's take the case of Boston dataset from mass package and extract the principal components. The PRComp function computes the principal components, and we have turned on scaling. PCA_out shows the loadings used to calculate the principal components. Loadings are like beta coefficients that are multiplied with each feature to compute the principal component values. But it also contains the actual principal components inside it. Boston_PC has the principal components having same number of rows as the original dataset. By convention, the principal components are referred to as PC1, PC2, and so on. PC1 explains the maximum variability, PC2 lesser than PC1, and so on. The summary shows the cumulative variance explained by the principal components. Let's plot it. This is the graphical representation of the information in the summary, where x-axis represents the PCs. The principal components can also help visualize how the features, as well as the observations, are related. This can be seen using the Biplot. Each number is a row in the dataset, and the points in red are the columns. The points situated together are more similar. Likewise, the columns that are close are more correlated with each other. We will see how to capture the group containing similar points in the next video. As in previous sections, let's do a coding challenge. Compute the principal components on empty cars. What percentage of variation is explained by the first two PCs? Good luck. So here's my answer. So the first two principal components explain about 84.17% of the variation. Congratulations if you solved that.